So as for my partner in crime sets up, since we have to just transfer video cables, because again, is this, that one? Oh, you forgot. Better? Yeah, okay. So as my partner in crime sets up the laptop, as usual, we're a special case because we have a small video that we'll play through. And also as constraints, I just got taught how to teaching students how system calls work and how exec loads process. So I promise I will try not to mix up the topics with that and what we're doing here. And both of us have to go to class right after this as well. So we'll try to be efficient since that's the claim of what we're after. Okay, so we talked a little bit about this yesterday. At least one of my graduate students did, or one of my postgraduate students did, that this question of being efficient with our resources. So this is actually a poster from wartime. It turns out that it's from Canada, from the Food Board. That is an elderly woman telling a young woman, hey, look, don't throw shit out. Take some simple precautions, do some canning. And at that time, it was quite simple. It was very clear that lives depended on efficiency. So let's figure out where we are today. So since I did just get out of the lecture, and since it seems to be in vogue, I thought I'd have this conversation with ChatGPT. So I asked ChatGPT, hey man, what's the energy cost of a Google search? Now in all fairness, I studied this a little bit, and I learned some fascinating things. While it is difficult to estimate the exact amount of energy used by a single Google search, it is safe to say that the energy consumed is very small. In fact, Google has stated that energy required to perform a single search is equivalent to the energy needed to turn a 60-watt light bulb on for just 17 seconds. Whew, that's nice. However, it's worth noting the energy cost of a Google search increases when multiple searches are run at the same time and in rapid succession, or large files are being downloaded. And then Google or ChatGPT goes on to tell me, additionally, the energy cost of a Google search, or Google searches, and other online activities may have a larger impact on the environment, which I did not ask it, when they are performed on devices that are not energy efficient or powered by renewable energy sources. That's fascinating. I didn't actually ask where the energy came from. But I thought, okay, surely ChatGPT, okay, fine, it doesn't know what Google does. How about its own queries? So I asked it, hey, what's the energy consumption of a ChatGPT query? So I'll save you all of this. But, it admits, however, it's worth noting that large-scale language models like ChatGPT are typically hosted, so, it's making up for itself, typically hosted on cloud-based infrastructure provided by companies such as Amazon, Microsoft, and Google. These companies typically use energy-efficient data centers and are committed to using renewable energy, which is, again, also kind of fascinating that it's actually doing a little bit of a duck, right? Which can help to reduce environmental. I didn't ask any of that. I'm pointing out that it is just a good idea to save resources, independent of your political slant. And would also like to point out that, hey, likely that the energy consumption would be relatively low compared to other energy intensive activities, such as transportation or the industrial production. Wow, that's also cool, right? I think what I just found out is that, no offense to lawyers, politicians, and marketing people, that they have actually populated the internet. So I thought I'd better ask one more question, because it seems to me that data centers are at the heart of what we're depending on. So I asked ChatGPT, what is the global energy use of data centers? The global energy use of data centers is difficult to estimate. Wow, ChatGPT really always has a hard time. But is widely believed to be a significant and growing contributor to global energy consumption. So now it goes on to tell me that an expectation is, so right now it's 1%, and that by 2030 it's expected to be 651 terawatts, and right now it's 194 terawatts. But largely, it still comes down to this statement: services requiring large amounts of computing, power, and data storage, which in turn require energy-intensive IT infrastructure, including servers, networking equipment, and cooling. So, in the end, I argue that the notion of making our data centers efficient, independent whether it comes from renewable energy or not, which is all the vogue for my colleagues to claim, well, it doesn't matter. Imagine what we could do if there were just some simple things, like canning, to save on the energy consumption. What could we do with that savings? Whether it's a reduction in footprint, whether it's a reduction in cooling, or actually spending that money on other things, like food production. Okay, so we've been playing around with trying to understand if there are some simple things we can do. And what we have been discovering is quite interesting. That in the end, if you start studying a system, and you say, look, all the software and all the hardware combined, independent of what kind of software it is, we should just study it and think a little harder about how it behaves. So let me set this graph up a little bit. So on the y-axis is joules. So we measure the actual joules consumed. Now, we are measuring it on processor meters, not at the node. However, we have seen these numbers bear out. Savings that we show here translate into savings on the node level. So, now I've got energy on the y-axis. What I'm going to do is I'm going to take a memcached workload, so a memcached server, caches, all kinds of important data based on back-end web services to ensure that we can reduce the latency of web traffic, right? So it's a core operation that we run computers to do. And the nature of load, so queries per second, which is each graph here. So there's 200,000 queries per second, 400,000 queries per second, 600,000 queries per second, 1,000 and 1,500. That is the rate at which I'm throwing work to one of these memcached servers. The x-axis is a form of delay. But what I first just want to walk through here is that it should, I hope, be intuitive that if we batch work, right, we're all sort of used to this idea, that if I batch up work, there's an opportunity to be more efficient at it, right? All you gotta do is have somebody tap you on the shoulder every 15 seconds while you're trying to write, and you know that actually it's really nice to have somebody in front of your door stopping them from tapping you, right? So it's a good idea to be able to bunch up your time and work hard. Now that's something that we can actually control ubiquitously. It's not a phenomenon of a particular processor. It's not the phenomenon of a particular operating system. It's the phenomenon of this workload that I want to be able to just simply delay. Now, of course, I need to get my responses back at some particular time. That's why we did this whole thing, right? So we establish a threshold called an SLA, Service Level Agreement, or a Quality of Service metric that says I want 99% of all my requests to be satisfied within 500 microseconds. Remembering a microsecond is a millionth of a second. So, what I'm going to do is I'm going to study the system. Now, what I've got here is a Linux operating system configured with its memcached stack. Every point on the plot represents me batching the traffic by some factor. In other words, I just stop and I say, hey, you're not allowed to actually process for a while. You don't even know that the work is there, and then I'm going to release it. At the far end of the curve, well, actually, what I see happening is I change this batching factor. The 99% tail, which is the x-axis, I am seeing that what happens is on the green curve, right? I am reducing my energy consumption while roughly staying in the same range of 99% tail latency. As I move further down, and all of these are meeting my SLA requirements, right? Because I'm cutting the graph off. So I'm seeing that simply from the outside, changing the rate at which work is received, I can actually make quite a dramatic impact on the system's ability. So let's dig into this, and we call these kind of business behavior as a sweet spot. And just to make sure that we weren't bullshitting ourselves, we used a different operating system as well that was custom designed for this work. And so yes, that's the red curve. So yes, while it is better because it was designed just to do this job, it still behaves the same. And actually, it has a broader range. You can get up to higher QPSs where it doesn't fail, but it still actually has sweet spots in its behavior. So, in the interest of time and my office hours, I'm just going to briefly discuss what it was that we found scientifically that we believe is ubiquitous control that we can play with. Now again, in all fairness, the workflow that we've been working on is pretty highly regular, right? It's a server running memcached. We also did things like memcached silo, so that we actually added computational work. We also did the idea of, these are called open loop, right? So the requests are coming in independent of what I do. But of course, there's closed loop work too, right? Where I get a request, I send a response, and then the other side can send me a request. So that's the two basic categories. So just keep in mind, this is quite limited in terms of what we're exploring. But, so it turns out, all the way back to the 1960s, when we started introducing the idea of high-speed I/O, it was very obvious to us that we needed to be able to throttle that tapping on your shoulder, the interrupt rate, right? Remembering everybody, an interrupt is when something happens on an external I/O channel, it causes me to go, shit, I gotta go pay attention to it, right? And so the OS has to come over and pay attention. And that's how I actually find out that I have packets. So all modern NICs have a feature that enabled what's called interrupt coalescing, which just simply says, hey, I know that it takes me some time to dispatch an interrupt. I better not let that overwhelm me. But it turns out that very same control effectively lets me batch more ubiquitously, not just to avoid interrupt overhead overwhelming my time, but actually just simply control the rate at which packets are available for processing. Okay? So that's the top, right? Now, the other control that we're all much more familiar with, that we understand from an energy processing perspective, is the fact that processors have inside them various controls that let me control two things. The frequency, and a combination of frequency and voltage, called a DVFS, right, dynamic voltage scaling, because we know that the physics of a CPU, that if I can change either the voltage or the frequency, slow it down, I can reduce its power consumption. Now it turns out in a modern processor, that's all well and good, but we also just leak crap loads of energy for things like our caches. That's our static component, right? That's why we have idle states, right? So processors like Intel and Ampere have states that the software can say, put me to sleep. And as it puts it to sleep, you can dramatically reduce the static cost while it's not busy. Of course, you have to be software to know it's not busy, right? Because I, as the OS, have to go, shit, I got nothing to do, let's go to sleep. What state should I go to sleep in? Well, I don't know. Let me have an algorithm and let me guess. Now, the interesting thing is, as I go to a deeper sleep state, how am I achieving that? I'm flushing the caches because I'm going to turn them off because they suck up a lot of energy. But of course, I flush the cache. So what's going to happen to my performance when I come back? It's going to be slower. So there's all kinds of complicated trade-offs here. A lot of these algorithms are embedded in the OS. But it turns out that if I control these two things, so in this chart here, what I've got is, again, Memcache mean out a fixed query rate, 600,000 queries per second, and I've got time on the x-axis. Now what I'm doing, I'm actually showing effectively power consumption. It's energy consumed per second. So I guess office hours really is going to go late, sorry. So what I'm showing here is that we control these two controls for the same rate. I'm showing what's happening instantaneously with respect to power consumption. And what we find is two different controls, the ITR and DBX combined, produce radically different instantaneous behavior while the system is running. Independent of me not caring at all about what the OS thinks, I can trick the OS to find and operate in these sweet spots. I'm not going to talk about this. This is the underlying data from the prior chart. This is actually showing that there are plenty of points that perform well and bad. And finding these sweet spots and exploiting them, which surely that should just be a trivial job. So as a final thing, so that we can move on to talking at least for a few minutes about stream computing, what we did to exploit this is we said to ourselves, well, look, you want to set these knobs very carefully. It has to be relative to your arrival rate, so the rate that work is coming in, relative to your operating system, relative to your hardware, to your NIC, all of it, okay? So that means that as the world changes underneath you, you have to be able to find the right setting. So what we did was we took a Twitter trace on a Memcache D cluster, and then we said, look, this is the load, so queries per second, and you see that it's very stable, the mean load. And so what we did was we said, hey, why don't we build a smart agent and who can go query the machine, figure out what it's under, and set these two values into its sweet spot. I'm not going to talk at all about how that works. Instead, what I'm going to do is I'm going to simulate on one of our servers that load rate that changes, the mean load is roughly changing every hour. I'm going to trigger my magic box to go examine the machine in situ and set the ITR DBFS. And what I find is, so it's energy on the left, time of now the Twitter trace at the bottom, and the queries per second are varying. The blue bar is the energy consumption of Linux on its own. The green bar is the energy consumption of us controlling. The difference, that's your canning factor. That's us simply getting the work done within the SLA with lower energy. Because all we did was intelligently try to do the right thing. Don't be an idiot. Don't just service your request because they came in. So, with that in mind, this is all well and good, but there's a lot of open questions. We believe the controls are ubiquitous. We believe that the phenomenon holds, but can we actually make it work for more complex things and, in some sense, the real world? And so with that, instead of being...
Okay, hi everybody. I will be brief, indeed. So the reason I like working with Jonathan is because he gets so excited about his research, as you can tell. Basically, these results are very exciting, and we want to see whether we can port them to a more challenging workload and a more challenging software stack. So we are working towards applying the same techniques, or porting the same techniques, extending them to a stream processing system. So for those of you who are not familiar with data stream processing, think of turning a database inside out. We are used to this model of having our data stored somewhere and then sending queries to this data. So think of this model flipped, like you have queries that are long-standing, right? And then you stream data through them, right? So these are long-running continuous computations. And in fact, stream processing analytics is an area that is growing a lot over the last years. There are some projections there from a few market research studies. So by 2025, more than 30% of data of the entire data sphere will be real-time data, so streaming data, and the business of streaming analytics, the market size is really growing. And also data stream analytics as a service is really growing, so most of the cloud providers today offer streaming analytics as a service. You might recognize some of those, or might be using some of those. You are actually using stream processing in your daily lives through your apps, even if you don't know. Here are some examples, so recommendations, traffic management, even support for deep space network explorations. But in terms of science and why we care about these workloads is because they are much more challenging than the Memcached ones. So the Memcached application is very lightweight. You have one server, you send queries to it. These are like different beasts. They're really large distributed systems. They are usually built on top of the JVM, and there are layers and layers of software that a request or a packet needs to go through before it arrives on the other side. So what we want to explore in this project is whether we can make sense of all of this complexity and actually relate it down to the operating system configuration logs. This is, I don't know if that's going to play, but this is essentially me just scrolling down a web page for configuration options in Apache Flink, the system we're using. So as you can see, it's endless configuration options that an application developer needs to tune. And at the moment, we don't understand at all how this application level configuration tuning interacts with the operating system or the hardware. So this would be like one of the outcomes, hopefully, of this project. There are a bunch of other challenges in stream processing. One of them is dynamic and unpredictable workloads. The main solution today is to just throw resources at the problem. Most people will just over-provision and overpay at the same time. Correct. Summarizing, I know we're way over time. So we want to achieve high performance energy efficiency in open source stream processing using an OS-centric approach. We are already gathering and curating and publishing small data sets of these measurements. We want to come up with a set of tuning guidelines for configuring the system and automating optimization. We have already a test bed running. Actually, Sana is here in the back, our PhD student, and she has a poster, so you can go and talk to her about our test bed and our current experimental setup. We have some preliminary results that, again, are open and public, and you can look at them. We think that this is work. This is a long-term project, so at least PhD thesis and maybe a postdoc, one from the streaming side and one from the OS side. We would love to have also access to representative platforms and state-of-the-art networking infrastructure that people are using, as well as access to industry experts who provision and manage these kind of streaming platforms. That would be very valuable to us. That's it. Thank you very much.